All right. Good morning, everyone. So we'll get started. Again, the reminder items will be homework due tonight. Okay, so a couple of you guys haven't finished. Make sure you finish them by midnight tonight, and then the solutions for this homework set will be available online. Will be visible online. Actually, for you guys, it's online already, but it's not visible currently. So be visible to you guys after midnight tonight. Okay. Um, Also, I want to point out for the exam 3 this Friday, it covers mainly chapter 7 through 10, and then also the first section of chapter 11 on rolling motion. Okay, so chapter 7 through 10, and then first section of chapter 11, or the same content in the homework assignments 7 through 9. Okay. I also have number 10 assignment up online now. It's due on next Wednesday. Okay, so if you guys after the exam you can start working on this. Or for now, if you are ready for the exam, you can also work on that too. Okay. So today we'll be finishing chapter 12. There's one content remaining in chapter 12. We'll go through that briefly. And we'll also look at chapter 13. Okay, so part like a few sections in chapter 13. So we'll finish chapter 12 today, and then also start chapter 13. Okay. All right. So last time in chapter 12 we talked about static equilibrium. So this time we'll just briefly going through elasticity. Okay. So um, for most of materials, if you apply force, okay, if this is like one-dimensional material, like it's very thin and it's long, you can apply force at the end. So either you are stretching it or compressing it. So then the length of the material will change slightly. Okay. So this change in shape due to application of force, we call it deformation. Okay. So I think we are pretty much just going through a few terminologies here. I believe if you guys are taking a class like called materials or mechanics of materials later on, or you are taking it, you will get touched to more of this. Okay, but so this is deformation defined as change in shape due to application of force. All right, and then the elasticity is the measure of deformation of object when a force is applied. Okay, so um, all right, so let's see. So if you apply a force F, then length will be changed delta L. Okay, or if you apply this suppression force, then there'll be change in delta L as well. Okay, so then this is the same magnitude for of the tension or compression. Okay, so this is proportional actually. So if delta L will be proportional to F. Okay, and so deformation also depends on materials. If you have different materials, then under the same force, the change in the shape will be different. Okay, so if you have, for example, a thinner material, okay, so then this is the nylon, so then it will probably stretch more than this guy here. If this is a thicker, okay, so you can see it also depends on cross-sectional area. Okay, so thin material stretch more than thick material. Okay, and then if you have a different material, then it's going to be different as well. Okay, so it also depends on material. If you look at this one and this one, they might have the same thickness, but because the materials are different, so then stretch amount will be different. Okay. So this delta L, the change in shape, is proportional to force applied, inversely proportional to the cross-sectional area L A, and then L naught is the original length. Okay, so it's proportional to also L naught, and then it's inversely proportional to this Y, capital Y. It's called the elastic modular or Young's modular of the material. So given a certain material, this Y is a fixed number. It's kind of like property of material. Okay. So sometimes you can also determine the Young's modulus to determine what's the material if it's unknown. All right, so then delta L equals to 1 over capital Y times F divided by A times L0. Okay, so basically, if you rearrange the question, the equation, you put the area to the other, the force and the area to one side of the equation, and then the rest on the other side of the equation. Okay, so then you will have this. So this is basically rearrangement of the quantities in the equation in the previous slides. Okay, so the F over A is defined as stress. Okay, also in the second semester, you will know that F divided by A is also called pressure. So sometimes we use these two terms like interchangeably. So sometimes you say you are under stress, sometimes you say you are under pressure. Okay, so in physics, these two terms actually are defined the same. So it's both F divided by L. They are both defined as F divided by A. Okay, force divided by the area and under the influence of the force. All right, and then the other side of the equation, delta L divided by L, this is called strain. So stress and then strain are proportional to each other. So stretch is equal to Y times the strain, okay? And so now if you apply force, if your applied force is increased, okay? So you will see for material, if your apply force is small, then this change deformation delta L will be linear to the force you apply. Okay, now if you increase the force to a certain area, then it's not proportional to the force applied. All right, and take example for a rubber. Okay, you can actually apply force for the rubber, then stretch amount will be initially like proportional to F and then not so linear to F. But still, if it's not large enough, you can actually, after you release the force you apply, the rubber can return to its initial shape. Okay. Now, if you keep increasing your force, at certain point, the deformation is going to be permanent. Okay. So that means even you release the force you apply, then it's not going to return to its original shape. So deformation is going to be permanent at that point. If you keep increasing the force, then at certain point the material is going to break. Okay, so then fracture will start to build up at there, and then initially will break. Okay, so for the spring force, the force by the spring, it's in the region of the Hooke's law here, where it's change in length is proportional to force. Okay, so that's the thing we use. Okay, so then Hooke's law is equal to K times delta L. Okay, I think you're more familiar with the expression of F equal to K times delta X. Okay, so that's the same thing. It's the change in length over there. Okay, so it's basically, again, starting from this equation from deformation over here, deformation equals to 1 over YF times A times L0. And then you rearrange the terms, so then F equals to K times delta L, where K is equal to Y times A divided by L naught. Okay, so these are all constant terms. So those terms determine what's the spring constant. Okay. So that's when you apply force in one dimension to the material, and you can also apply force sideways to a structure. Okay, so for example here, so then if you're applying the force in this sideways, so then sideways stress is called shear modulus. Okay, so then you will have deformation in the sideways. Okay, you can also apply force in three-dimensional. So then there will be change in shape of the object. So all the volume will be changed. Okay, so then that's called bulk modulus. Okay, we are not going to discuss details of these scenarios over here, but that will be it for the general physics class. Okay, so that's this chapter. So I'm gonna to share with you chapter 13 for the PowerPoint slide. All right. So in chapter 13, we are going to look at pretty much so this is, again, it's just like introduction, kind of like introduction to astronomy. Okay, so although astronomy may cover a lot of more contents, but this will be something related to astronomy. So it's the gravitation. Okay, so basically gravitation, that is the gravitational force. It's universal to any two objects in the universe. Okay, so even like two persons or like two whatever objects, maybe stars, maybe galaxies. Okay, they are interaction between them. One of the interactions between them will be the gravitational force interaction. Okay, so this is then Newton's law of universal gravitation, which Newton proposed that there's attraction force between any two objects in the universe, and then that force is equal to a constant number called g, the gravitational constant, times the mass of the two objects. Okay, so a capital M, small m, and then divide by the separations of the two objects score. Okay, so we will be referring to the center of mass, separation between the center of mass of the two objects. Okay, so this is Newton's universal gravitational law, F equal to G times capital M times small m divided by R square. Okay, so and this G is equal to 6.674 times 10 to the negative 11. That's in newtons times meter square divided by kilogram square. Okay, so so G actually is experimentally determined. Okay, so it will be a lab we can do, but it's at really challenging. Okay, so it will be very easily being distorted by other like other factors. Okay, for example, someone is walking in the hallway, or maybe a car is driving by, etc. But basically, if you can have a very good environment, you can, this is what you can do. You can have a fiber optic or fiber here that is having a mirror over here, and then you have originally these two small masses. Okay, now you can have a light source shining on that, and then so there's an angle between this light path and the normal direction of this mirror. And then somewhere here, you can put a meter stick or scale here. Okay, so there's original light will original shining on a spot on the scale over here. Now you can move these two big balls, big masses, close to these small ones. Okay, so with the center being at the line of this fiber here, and then the two are equal distance away. Okay, and you can measure, you can set the distance of this two ball and this two ball. Okay, so you can see then there will be attraction between these two, and then attraction between these two. Okay, then there will be force that it generate a torque. Okay, which will make this rotate to a certain angle position. Okay, so the angle will be changed. Then this guy will be shining at a different spot at the scale over here. Okay, you can monitor what's the torque in the fiber here. Then you can actually calculate what's this G. Okay, but it's a very challenging lab to do. Anyway, the G is this number. Okay, so you can look it up in a problem if it's not given. All right, so due to gravitational attraction, our own galaxy, Milky Way, and the nearest galaxy, Andromeda, they are actually predict to collide with each other in 4 billion years. Okay, which you and I will probably not exist in the world, but something will happen in that time frame. Okay. All right, so let's take a look universal gravitational law here for the example of two sumo wrestlers, each having having masses of 220 kilogram and 240 kilogram. They are 1.2 apart from their center of mass. So what's the gravitational force between the two? Okay, so it's basically F equal to G M1 M2 divided by R square. Okay, or if you want, you can use capital M, small m. Capital M and small m will be the masses of the two. Okay. All right, so yeah, pretty much just plug in the numbers, okay, and then into this equation over here. So m1, m2 are capital M, small m, and divide by 1.2 meters square. Okay, so just keep in mind that in the denominator over here, r, you want to square it, okay? So sometimes people forget about that. And then this is 10 to the negative 11 for the g, okay? So I think I see all the responses you guys have in are correct. So that's good, okay? We can move on to the next one. Looks like you guys are clear with this. All right. So I think one of the quantities we have been using quite often is the gravitational acceleration, and that's due to if so any object on the surface of Earth will experience gravitational force, right? The mg, and that's because the object and the Earth, so the center of mass of the Earth and the center of mass of the object, they are separated by about the radius of the Earth, and so then um, in that case, that this mg gravitational force is equal to the g capital M small m times r square. Okay, so in this case, you can see small m and then small m will cancel out. So then g is equal to capital G capital M divided by r square. Okay, so on the surface of the Earth, gravitational acceleration should be equal to g times the mass of the Earth divided by the radius of the Earth square. Okay, so we can actually use this equation to calculate what would be the gravitational acceleration g. Okay, so you guys can also give it a try. Just plug in g as the 6.674 times 10 to the minus 11, capital M as 5.98 times 10 to the 24, and then r as 6.38 times 10 to the 6 meters here. Okay. So g will be equal to capital G capital M over r square. You'll be plugging 6.674 times 10 to the negative 11. All right, that's newtons meter square over kilogram square times this guy 5.98 times 10 to the 24 kilograms divided by 6.38 times 10 to the 6 meter square. Okay, so then this will give you if you plug everything into calculator correctly, this will give you just roughly 9.8 okay, meters per second squared, okay, on that guy. And this equation, actually, you can use this equation to calculate or to estimate the gravitational or gravity on any of the planets given the mass of the planet and the radius of it. And then also you can calculate the gravity on the moon as well using this guy. Okay. All right. Now let's take a look on the example to calculate the acceleration due to gravity on the surface of the moon, the Mars. Okay, the mass of the Mars is given as this 6.418 times 10 to the 23, and its radius 3.38 times 10 to the 6. Okay, so give it a try and then see what's the gravity on Mars. All right. So yeah, again, we just plug in the numbers over here. And if we have everything in SI unit, we can leave the units out for right now. So let's do that. So mass of the Mars is 6.418 times 10 to the 23 divided by 3.38 times 10 to the 6, and then square that. Okay, so that's going to give you 3.75 meters per second square roughly. Okay, so most of you guys have this one right. All right, let me know if you have questions if you didn't get this right. All right, so the gravity is a vector. We know that, right? Because it's gravitational acceleration, it's an acceleration, so it's a vector. Now, it always points towards the center of the mass that causes it. So for example, if this is the Earth, then on the surface of our Earth is downward because that's the direction to the center of the Earth, okay? So if that's the case, then um, around surrounding any object in the universe, there's gravitational field by that object, okay? Because then anywhere surrounding it, if you place a second object, you will experience that force towards the center of this guy, okay? So then there's a field surrounded, okay? So this is called gravitational field. All right, and then a couple of years ago, you guys probably know that this for the gravitational wave theory that was confirmed by LIGO experiment. So basically, two black holes, big black holes, they merge, so they produce a large, massive um, object after the merge. So then um, surrounding this new object, it has large gravitational fields. This is like something if you throw a rock into a calm lake surface, so then it will generate the wave, right? So if such an event merge of black hole happens, then it will generate waves throughout the gravitational field. Okay, and that was detected by LIGO um, experiment a couple years ago. Okay, all right. So on the Earth over here, okay, because actually Earth has the rotation with its axis. Okay, so then the places other than on the poles, okay, where although it's having like the rotation, but near the pole, as that rotational is going to be zero because that radius is going to be zero, right? But other than that, any place other than the poles, then actually, or actually, yeah, right. That's right. So any other places, even on the equator, your weight actually, when you measure it, actually it's not exactly the weight mg, but there's additional of this rotational effect to it, right? Because say if we are somewhere here, so there's mg towards the center, but due to the Earth spinning, so we are actually having circular motion. So then there's a centripetal force in this direction. So the total force will be the sum of these two, that is read from the scale. Now this centripetal force compared to the mg should be very small. Okay, it's going to be like this guy. So this is if you do Re times omega square, that's the angular speed of the Earth's spin, rotation, Earth's rotation. So it's going to be contribute to the acceleration of about 0.0337 compared to 9.80. Okay, so this is small number. All right, so we can actually ignore it. But just keep in mind there's a little bit effect due to Earth's rotation. So then the whatever you measure is not exactly the real weight. Okay, it's slightly different. All right. Okay. So for the Earth itself, okay, so we say G is equal to 9.8, okay, but it actually, so if you actually going through inside the Earth, you will see that the mass of Earth actually is not distributed homogeneously, okay, so then it's not linear change of the um, the gravitational force if you would going inside the Earth. Okay, so G will be differently, all right, or it's not linear. Okay, so this is a more real variation of the gravitational force. Okay, for the if you have to go inside the Earth. Okay. All right, so let's take a look again on the gravitational potential energy. Potential energy U equals to mgy. Okay, so we mentioned earlier that gravitational potential energy will be just mgy. Y is where the vertical location compared to your reference of ground level potential energy. Okay, so if you have change of locations of an object from y1 say to y2 vertically, then there's change in potential energy. Okay, so now normally we will say that this G doesn't change in when we change um, the position of the object vertically, okay, from y1 to y2. If compared to the Earth's radius, y1 and y2, the change are not significant, then we can assume G is constant, right? But as we learned earlier, like G is actually equal to capital G, capital M divided by R squared. Okay, so if the change in Y is significant, then the R here from location 1 to location 2 is different, right? So we in that scenario, we cannot really use G as constant. Okay, so what you then have to do is, so say for example, a spaceship over here, certain height above the surface of Earth, if it changes orbital from one orbit to the second orbit, that higher. Okay, so this change of height might be big. Okay, so then when you calculate the change in gravitational potential energy, because the force, the conservative force of gravity, it's a function of this r distance or the y distance. Okay, so then you have to do integration. All right, so in that case, then change in potential energy is more accurately expressed in this result over here after you do the integration. Okay, so then it's G capital M, the mass of the Earth, times the mass of the object or the spacecraft, and then divide by 1 over r1 minus 1 over r2. Okay, so r1 is the distance from here, first orbital, to the center of the Earth, and r2 is from here to the center of the Earth. Okay, so then the expression for gravitational potential energy should be more accurately expressed in this term. So U equals to minus capital G mass of the Earth times the mass of the object near the surface of Earth, and divide by R, where's the distance between the center of the Earth to the center of the object. Okay, so this is a more accurate expression instead of just mg times y. Okay. So then in that case, conservation of energy equation would be also modified slightly. Kinetic energy terms, still you use the original expression 1/2 mv squares, okay? But for the potential gravitational potential energy, you change it to capital G, capital M, small m divided by R, okay? And then assuming the small mass is much less than this big M, okay? All right. So we will take a look this example here when an asteroid that is approaching the Earth. Okay, so the mass of the asteroid is 2.0 times 10 to the 13 kilogram. And then so it's originally 5.0 times 10 to the 7 kilometers away from the Earth. Okay, and it's heading directly towards the Earth with a speed of 2.0 kilometers per second at that point. Okay, so what will its speed be just before it hits our atmosphere, roughly 480 kilometers above the surface of the Earth? You can ignore the size of asteroid and then use the radius of the Earth as 6,371 kilometers. Okay, and I believe you do also need to use the mass of the Earth, which is roughly, so capital M is roughly 5.98 times 10 to the 24 kilograms. Okay, small m is the asteroid, 2.0 times 10 to the 13 kilogram. Okay, and the original distance 5.0 times 10 to the 7 kilometers from the Earth, you can assuming that is from the surface of the Earth. Okay, so you apply the conservation of energy again, and then figure out what's the new speed when it just hit the atmosphere. Okay. All right, so let's take a look here. So the asteroid originally is 5.0 times 10 to the 7 kilometers away. Now this radius of the Earth is this. Okay, so then R1 is going to be equal to the radius plus the 5.0 times 10 to the 7. That's in kilometers, right? So we want to multiply by 10 to the third to have this in SI unit of meters. Now R2, it should be similarly 6371 plus the height of the atmosphere 480 and then times 10 to the third. Okay, so that's R2. Um, so the only force is between on the asteroid would be the Earth's gravitational force, okay, which is a conservative force. Then you can apply kinetic energy conservation, okay, so using this guy, all right. Originally we use USMGY or MGI if you would like, but in this case it's the capital G M. Okay, so in this case, it's going to be minus capital G, capital M, small m divided by R. Okay, so that's the new equation. So then this conservation of energy becomes this. All right. It has a negative sign. It's because the gravitational force is doing positive work. Okay, so that means it reduces the potential energy. Now the assumption is at far away, very, very far away, the potential energy is equal to 0. Okay, so then U is equal to 0 and far away it's equal to negative then in that sense. Okay, all right, so that's the negative sign is because we take far away as the ground level potential energy. Okay, so then it's negative sign here and there. Okay, so if you are wondering why it's negative, that's because of the assumption. All right, so you are given V1 and you're looking for V2. Okay, so in this case, you can see actually from the equation here, you can see actually small m can cancel out across. Okay, so the mass of asteroid actually doesn't play a role here, right? So then you're looking for V2, you are given V1, so you want to isolate V2. So move this guy to the other side of the equation, okay? So it becomes 1/2 V1 squared minus G capital M over R1. Now minus becomes positive, okay? Capital GM over R2 equals to 1/2 V2 squared. Okay, you can multiply everything by 2, get rid of the 1/2 here, so then 2 here, 2 here. Okay, so then for V2 you'll take square root and then square root of all this left hand side. Okay, so it will be V1 square will be the 2 kilometers per second. That means 2 times 10 to the third meters per second square. Let me see. Plus or minus this one first. Minus 2 times 2 times G, 6.67 times 10 to the minus 11 newtons meter square over kilogram square times 6 or 5.98 to be the mass of the earth times 10 to the 24 kilograms. Okay, and then divided by R1. So I'm going to just say let's factor out 2 GM first, and then this will become 1 over R1. So 1 over this 6371 plus 5.0 times 10 to the 7. All big numbers here times 10 to the 3 minus, so this will be in meters, minus 1 over 6371 plus 480 times 10 to the third in meters. Okay, all this in the big parentheses, and then take square root of it. Okay, so it's a giant piece there. Let me see. It looks like in my original note I was forgetting the factor of the 2's over here. So I got about 7.9 kilometers per second. So that's probably not right. Okay, so let me double check with that. Square root of. All right. So it looks like it's more like going to be like 11. So V2 would be roughly 11 kilometers per second. Okay, roughly. All right. Now I might typing things wrong, so I'm not 100%, but it looks like more like that. Okay, if you get a different number, you can double check. If you still getting your number, then it's likely I didn't have everything right. Okay, but anyway, that's how you set up the problem and then solve for it. Okay. All right. Let me know if you have questions. So if not, then let's check the last topic of the day here on escape velocity. Okay, so um, so the total energy, like the kinetic energy plus the potential energy, is 1/2 mv squared minus g, capital G, capital M, small m divided by r. Okay, so in that case, that if you are launching something into the space, you are originally on the surface of the earth. Okay, so then this is original gravitational potential energy. And if you want let object to escape the earth, for example, then you need to have a initial velocity that's big enough. Okay, we call it the escape speed or escape velocity. So then this is the original kinetic energy. So if it can leave the Earth and then get rid of the influence of the Earth, that means it can go to very far away. So then R becomes infinity, right? And then at that point, you might be having zero velocities, but you are not going back to the Earth. Okay, so you are escaping the Earth. Okay, so then the total minimal energy will be equal to zero when this object escape the Earth. Okay, so this is then equal to zero. So then this guy will be equal to this. Okay, then you can solve for the escape speed from the Earth. Okay, so it's going to escape speed is going to be equal to square root of 2 times capital G, the mass of the Earth, divided by the radius of the Earth. Okay, and then if you plug in everything into this equation, it turns out to be 11.2 kilometers per second. Okay, in order to leave the Earth. Okay, now you can apply this equation onto any other planet. Okay, so for example, you can calculate what's the escape velocity on the moon by plugging the mass of the moon and then radius of the moon, or maybe from the Mars, and then that in that case you'll plug in the mass of the Mars here and then the radius of the Mars. Okay, so let's try to find the escape speed from the surface of the Mars. Okay, so the mass of the Mars is 6.39 again, times 10 to the 23 kilogram, and then its average radius 3,390 kilometers. Okay, so what would be the escape speed then? You guys can give it a try. We can take a look on the solution together in just I think a couple of minutes. That should be enough for you guys to calculate this. Okay. All right. So you need to plug in the numbers over here. For the R, it's 3,390 kilometers. So don't forget this is 10 to the third for the SI unit in meters. Okay. So if you put everything there, it should give you roughly 5015 meters per second. Okay. Or you can say about 5.02 kilometers per second. Okay. So either way, that'll be fine. Okay. So yeah, roughly 5 kilometers per second. All right. Okay, so I think that will be it for today. I will see you guys in class tomorrow. Okay, most of you guys. Okay, and then if you are in quarantine, you can join us via Zoom. Okay, so see you guys tomorrow.